This lecture covers the material discussed in chapter 11 of the book. The title of this chapter is Work, and before we start defining what work is and how we calculate work in different situations, let us just quickly look back at what we discussed in the previous chapter, which was conservation of mechanical energy. If you recall, we defined the mechanical energy of a system, E mechanical, as the kinetic energy of a system plus the potential energy of the system. And we said that if we have an isolated system, that is a system where there is no external force acting on the system, and that friction type forces are non-existent. So F external is 0, and friction type forces or non-conservative forces, sometimes called dissipative forces, are also 0. So if we have an isolated system, then we showed that mechanical energy is conserved, that is mechanical energy initial is equal to mechanical energy final, or the sum of the kinetic energy and potential energies before and after are equal. Now let us take a look and consider the scenario where friction type forces, these dissipative forces, are non-zero. In that case, if friction type forces do exist, then that leads to an increase in the thermal energy of the system. I'm sure most of you, or all of you, have experienced increase in thermal energy when friction is present. You can rub your hands together. The friction between your hands gives rise to an increase in the thermal energy. If friction type forces are do exist, then there will be an increase in the thermal energy of the system. So if Ki plus Ui is the initial total energy of the system, then in our final state we'll not only have a kinetic energy term, a potential energy term, but a thermal energy term as well. So now our total energy is split between mechanical energy and thermal energy in the final state. We can rewrite this equation and in this form, which sometimes helps in problem solving. So the change in kinetic energy plus the change in potential energy plus any change in thermal energy equals 0 if external forces don't exist. So kinetic and potential energy, that's our mechanical energy, and the change in thermal energy was brought about as a result of friction being non-zero, or friction existing. Now let us consider the case where external forces are non-zero. So there is an external force in the system. Rewriting this equation at the top here, we have delta K plus delta U plus E thermal must equal, so rather than 0, now we have what F external does on the system. And it's that what it does on the system, what F external does on the system, is what we define as the work done by F external. W here stands for work. So our equation takes the form of delta K plus delta U plus delta E thermal equals work done by F external. Now notice that on the left hand side of the equation we have energy terms, the units for which are joules. So by definition, work also has the units of joules. We must balance our units, of course. So now this is a more general form for the conservation of energy statement, where the total energy of the system equals work done by any external forces on the system. Now let us see exactly what this means. Let us consider this scenario. Let me switch my pen. We have mass m, which as a result of which is has an initial velocity vi, and as a result of a force F which is acting on it. Force F acts at an angle theta with respect to the horizontal. So as a result of this force F acting on it, our mass gets displaced through SF minus SI, that's our delta S. Okay, gets displaced through delta S along the horizontal direction, and achieves a final velocity Vf. Now let us assume that friction is zero. Now in this situation everything is along the horizontal. The motion of the displacement rather of the object is along the horizontal, therefore change in the gravitational potential energy of the system is zero, because its displacement is along the horizontal, and there is no spring involved, no spring force involved, so change in the spring potential energy of the system is also zero. So about the only thing that changes here is the kinetic energy of the system. Friction forces are zero, which means that there is no increase or change in the thermal energy of the system. Now, let us write Newton's second law, which states that force along the s direction, so this is the s direction, so the component of force along the s direction must equal mass times acceleration along the s direction. Our object only has acceleration along the s direction, as. Okay, although the force is applied at an angle theta with respect to the s direction, nevertheless the displacement and the resulting acceleration is only along the s direction. Now as we can rewrite as the rate of change of vs over dt, where vs is the velocity of the object along the s direction. Using the chain rule in calculus, we can rewrite this equation as m dvs ds times ds dt. Now we note that ds dt, the rate of change of position of the object, is nothing more than vs. So now I can rewrite this top equation in this form. Fs is equal to mvs dvs ds, which allows me to, by bringing ds from the right hand side over to the left hand side, to write Newton's second law in an integrable form, where integral of Fs ds over the limits of initial position to final position is equal to the integral of mvs dvs over initial velocity to final velocity. So that's an integrable form of what we started with, essentially f equals ma. So on the left hand side, let us keep this term as is, and on the right hand side, doing a quick integration, we end up with 1/2 of m times vf squared minus vi squared. Now 1/2 of mv final squared is nothing more than the final kinetic energy, and 1/2 of mv initial squared is our initial kinetic energy, i.e. the right hand term defines the change in the kinetic energy of the system. Now if you recall, we had said that the change in the kinetic energy plus change in the potential energy plus change in the thermal energy of the system we define as the work done by F external. And in this particular example, we argued that change in potential energies were zero. There was no friction, so E thermal was zero, which leaves the change in kinetic energy is equal to work done by F external. Therefore, the term on the left-hand side is an expression for work done by F external, which in this case is F along the direction S. So this is our general expression to calculate work done by a force, which says that if you have a force F being displacing an object through displacement delta S, then work done is the integral of the parallel component of S to of F rather, the force F to the displacement delta S over the displaced interval. Now, if the displacement is along a linear path, then this integral has a simple expression, which is simply F cosine theta delta S. So, for example, if you have, oops, didn't mean to go that far down. So, for example, if you have a mass here, mass M, which as a result of a 10 Newton force, which is applied at 30 degrees along the horizontal, moves through a 2 meter displacement along the horizontal, so that our delta S is this 2 meters. Fs, which is the parallel component of F, so Fs is parallel component of F, which is F times cosine of 30 degrees, and the work done by this external force, which is our 10 Newton force, is Fs, this once again this term here is Fs, times delta S, which is 2 meters in this case, which turns out to be 10 newtons times cosine of 30 times 2, whatever that value comes to be, joules. Alright, so that's the work done by force. Now this, you can use this expression of F cosine theta delta S if you have a constant force, but if the force is not constant, then you have to resort to integration forms. By the way, this have to make sure that you consider the product of the parallel component of F along the direction, along the displacement direction. So if you have a constant force, then you can go ahead and use this expression to calculate the work done by an object. So if force, this is our force vector here, and this is our displacement vector here, delta S, work done is simply F delta S cosine theta, where theta is the angle between the force vector and the displacement vector. This is also called the vector dot product. Vector dot product is a scalar entity. So if you have two vectors, vector F and vector delta S, and the dot product will give you this F delta S cosine theta. If you have your vectors, if you know the x and the y components for each of your vectors, then F delta S cosine theta is equivalent to fx times delta Sx and Fy times delta Sy. So if you remember, you could write your vectors in the form of its x component, this is in the unit vector form, I plus Fy j, and delta s similarly is delta s x I plus delta s y j. So if the vectors are given in the unit vector notation, or you know the x and the y components of your vectors, so you don't know the angle theta, for example, then you can use this expression here of the vector dot product to calculate work done by force F to displace the object through displacement delta S. So if our force vector, for example, is 2i minus 1j, and our displacement is 1i minus 3j, then the work done by this force to displace the object through delta S is the vector dot product of these two vectors, which is 2 times 1, that's this here, right, plus minus 1 times minus 3, which is equal to 2 plus 3, which is equal to 4 joules. So work done is 4 joules. It's a scalar result. Work is a scalar number. It has no direction, and that's why we use the vector dot product or scalar product. Now, in doing your vector dot product, the rules to follow is that I dot I is 1, j dot j is 1, I dot j is 0, and j dot I is 0. So if you dot I with the j component, then that's 0. That's why you only consider I dot I and the j dot j components. Excuse me. Now let's consider the same motion. So once again we have our object, which as a result of an external force F being applied to it displaces through delta S, and its velocity increases from Vi to Vf. But now let's say that there's also friction. The friction force, the direction of friction force, of course, is opposite to that of the displacement of the object. So now in a similar analysis to what we did before, we can show that the change in the kinetic energy of the system is equal to the work done by our external force, which was this integral as we showed before, but we also have yet another force that does work on the system. So change in kinetic energy is equal to work done by external force plus work done by friction force. Now what is this work done by friction force? Well, the work done by friction force, we said, is equal to negative of change in the thermal energy. So if we plug this expression into our equation here, we end up with work done by F, which is our external force, is equal to delta K plus change in delta E thermal. If you recall, this is what we started with back here, where we had of course, in the example I'm considering, UF is 0, so change in kinetic energy plus change in thermal energy is equal to, I'm sorry, this is the expression I'm after. Change in kinetic energy plus change in thermal energy is equal to the work done by F external. In the example we're considering just now, delta U is 0, but if delta U were not 0, then this whole change in kinetic plus change in potential plus change in E thermal is equal to external work done by the external force on the system. So in this example, we have work done by external force, F is equal to change in kinetic energy plus change in the thermal energy, and the change in thermal energy is the negative of work done by friction force on the system. Now, what is this friction force? How do we calculate the friction force done on the system? I think I have it right here.